Hi everybody, welcome to section 1.3 in differential equations. Direction fields. So previous section we define a differential equation and how to verify a solution of differential equation. This is one way to actually find a solution. Not the best way, but it's a way to do that. All right, differential fields. So one technique to use visualizing the solution of differential equation is what we call the direction field, which is a field of direction. Right. If we plot a short line segment at different points on the xy plane, and that we call the direction field. So pretty much a field of all of the little slope. And why slope is so important? Because the slope is the derivative. So pretty much we plot a bunch of derivative at each point of the function of the equation, right? And then when we plot enough those little slope, we can see what the solution might look like. It's kind of difficult to come up. We have to draw a lot of different slope in order to see the solution. Right, let's see how it works. Right, consider the equation y prime equal to x squared. Right, I choose a very simple example so we can verify the solution easily. Right, now after that we sketch the direction field, and after that we draw the solution for the initial value problem of this initial value problem. Right, so how do we graph them? So y prime equal to x squared, meaning y prime is derivative and derivative is the slope. So pretty much we will plot the slope for every point. Right, easier to set than done. Right, for example, we just pick a random point. Usually we just make a table. In the old days, we actually have to draw each one of them by hand, but I draw this by a computer program. So let's say we have x and y, and after that we just write y prime. Yeah, just make a table like that. I'll just pick some values. For example, when x equal to 0, y equal to 1, y prime is equal to x squared. So y prime equal to 0 squared, so that equal to 0. So at the point x equal to 0, y equal to 1, x equal to 0, y equal to 1, the slope is equal to 1. Its slope is equal to 0, which is the horizontal line. So draw the slope like that. Next, like I said, I will do that for every single point, and that's exactly what we come up with. Now let's see, when x equal to 1, y equal to 1, the slope is x squared, so be 1 squared still 1. So at the point x equal to 1, y equal to 1, the slope is equal to 1. So y equal to x, so that is the diagonal line. Let's do something else. How about some negative? Negative 1 and 1. Y prime equal to x squared, negative 1 squared, still 1. So at the point x equal to negative 1, y equal to 1, the slope is also 1. So we're going to draw a bunch of those little arrows. Let's try one more. 2 and 3. Y prime is equal to x squared, so 2 squared is 4. So at the point x equal to 2, y equal to 3, slope equal to 4, so kind of. Right, like that. and then we have to draw that for a bunch of pawns to have this view. Right, so after a bunch of them, we see the pattern. It looks like the solution, kind of like this. There are more than one, of course. It could go like that, but it looks like that. Those are the parent of the solution. In fact, it is, because if y prime equal to x squared, integrate, we will have y equal to the integral of x squared, which is x squared over 3, x cubed over 3, sorry, plus c. So the graph look like the x cubed of something. Right. So, like I said, but the solution, not by solving it, but by actually plot on every single point. And kind of difficult to do that by hand. Now, if we draw the solution of x squared and y with the initial condition y of 1 equal to 2/3. So actually we have two. Kind of difficult to see this, but so the solution it look like the x cubed plus c. So we might have something like this, and so we're just going to pick the one that when x equal to 1, y equal to 2/3. So this point is equal to this point here, x equal to 1, y equal to 2/3, and the cubic function that go to that point, x cubed over 3 plus 2/3, or some whatever the function is, it will go to that point. So we just graph, and that's what the solution. So like I said, we have to draw a bunch of these little arrows to get a clue what the function look like, and then we just kind of trace it, go to that point, and we have the solution. Like I said, this is just visualize the solution. There's no way we use this and actually come up with the solution, especially by hand. Right. One thing to help us to graph all of this, because we're not going to graph all of those points, that will be too much. What we can take advantage of this, what we call the isoclines, is the setup on the point on the xy plane when the solution have the same slope. So it could be a straight line, it could be anything. But on this example, y prime equal to x squared, you see that it doesn't matter what we choose for y. X is the determinant factor here, because y prime, the slope only depends on x. So in that case, everything on that line, everything on the vertical line, we have the same x values, therefore have the same slope. So you can see the isocline, I have a ruler, right? Okay, right here. So everything on this line have the same x values, therefore the same slope. And you see everything on this line, the same slope. So those are the isoclines. It's vertical line because they have the same slope. Only depends on x values. Y is irrelevant. That's why y can be anything. Right, like I said, kind of difficult to do this problem by hand, even with the isocline. Right, let's look at one example and see who can do this. Use isocline method to sketch the direction field for this equation. So in order to find the isocline, what we will look at is whenever this equal to a constant. So if we have x plus y equal to constant, then we have the equation y equal to minus x plus a constant. Let's see, write that as c, where c is a constant. So on this equation, on this line, the slope is a constant. So let's look at that. Let's see, equal to 0. Then we have the equation y equal to negative x. So when y equal to 0, when c equal to 0, y equal to negative x, which is this equation, this line. And on this line, what is the slope? C, which is 0, right? So we just say every point on this line, the slope is 0. So horizontal line, slope is equal to 0. Right. And then next, if we choose c equal to 1, we have y equal to negative x plus 1. So on the line y equal to negative x plus 1, the slope equal to 1. If the slope equal to 1, that means it is the diagonal line. So I will draw different color here. Let's say that slope equal to 1. And then c equal to negative 1, y equal to negative x plus 1. Minus 1. Slope equal to minus 1, so it will be that. Right. And I'll just keep doing that. Now when c equal to 2, slope equal to 2, a little steeper. And I will just keep doing that. But that's the idea. Like I said, usually this kind of problem, this A and H, we're not going to draw it by hand. But that's the idea. Just find where the slope are constant. And we draw that graph. And then the slope will be constant on that line. It could be a line, it could be a curve. Right. The calculator we have here, a TI-84, won't be able to do this unless we have to program it to do some certain things. So a TI-86 or TI-89 can do the slope field, but not the TI-84. It's that one cannot do it. Right. So like I said, on this day and age, we're not going to do this by hand. Some more example. Consider the autonomous equation. This is autonomous equation where we have the slope depends only on y, only on the dependent variable. So the only equation we have only depends on x, on the independent variable. This one depends only on y, and we call that autonomous equation. On this one, when we look at this equation, the function on the right have the signs follow. So how do we know that? Right, very simple. Just graph it, right? Let's just graph the function y equal to, let's say, x 2 minus x. See the graph, right? So, and the function, and if we graph, I'm going to draw very small here. this is the function y equal to x 2 minus x, parabola that open down. So between 0 and 2 it is positive, and on left side 0 and right side 2 it's below the x-axis, so it is negative. So in terms of the slope, if it is above 2 it is negative, so you can draw the negative line. And now look at the y-axis. If it is above 2 we have the negative slope, so that's going down. If it's positive, from 0 to 2 the slope is positive, because we have the slope equal to that. If the slope is positive it's going up, and when less than 0 it's going down, right? So the slope is positive, meaning it's going up, and the negative is going down. So we look on the right hand side and to see where the function is positive, where the function is negative, and then the slope equal to that. So if it's positive it go up, if it's negative it go down. In this case we see the solution converge to this line. We call that a stable equilibrium, and as x increasing at 0 the solution going away from it, so it's called unstable equilibrium. Right, that's just some terminology in related to the slope and direction field. But like I said, we don't do this, we don't do a lot of this problem by hand. This kind of problem though we see a lot, but the direction field itself won't be able to do that by hand, especially like in 2 hours test. That's impossible. But at least you get some idea about the direction field. Right, so that's all I want to cover for this section. See you in another video in differential equations. Thank you for watching.